For most of human history, food did not survive because it was kept cold. It survived because it was kept alive. Long before compressors, electricity, or ice houses, people learned that certain foods lasted longer when they were deliberately allowed to grow something on them. Not the kind of growth that smells of decay, but a controlled, repeatable transformation that stopped rot in its tracks. Entire communities depended on this knowledge, passing it down quietly through kitchens, smokehouses, and cellars. When done correctly, food did not merely resist spoilage. It became more stable, more nutritious, and safer to eat months later than it was on the day it was prepared. This was not luck or superstition. It was one of humanity's earliest biological technologies, and it worked without refrigeration because it changed the rules of decay itself. Why ancient people trusted fungus more than cold storage? Cold only slows spoilage. It does not stop it. Ancient people understood this through experience, even if they lacked modern terminology. Meat left in cool weather still rotted. Grain stored in damp conditions still molded unpredictably. But certain molds behaved differently. These fungi colonized food quickly, consumed available sugars, altered acidity, and produced compounds that hostile bacteria could not tolerate. Instead of competing with rot, they replaced it. Once the right fungus established itself, harmful microbes simply had no space to grow. This is why fungal preservation emerged independently across cultures separated by oceans. The method was reliable, repeatable, and required no fuel once mastered. Not all mold preserves food. Ancient cultures learned to distinguish between destructive growth and protective growth through observation and survival pressure. So, protective fungi spread evenly, smelled clean or kind of nutty, and stabilized food instead of liquefying it. These fungi actually formed physical barriers, consumed oxygen, and regulated moisture. In practical terms, this meant that food stopped changing rapidly once the fungal network took hold. European cheese rinds, Asian grain ferments, and African cereal pastes all rely on this principle. The fungus does the work that refrigeration does not. It actively defends the food rather than merely slowing its breakdown. In East Asia, molds such as Aspergillus oryzae became foundational to food preservation. This fungus breaks starches and proteins into stable compounds while preventing spoilage organisms from surviving. Cooked rice or grains were cooled, inoculated with a small portion of active culture, and kept warm for 1 to 2 days. Once the fungal growth spread, the grain entered a preserved state. From there, it could be salted, dried, or fermented further into pastes and sauces that lasted months or years without refrigeration. Modern viewers can apply this knowledge by fermenting grains into dense pastes stored in cool, dark spaces, creating shelf-stable nutrition without electricity. In medieval Europe, fungal preservation made protein storage possible even when salt was limited. Dry-cured meats were hung in cellars where airflow and humidity encouraged specific surface molds. These molds regulated moisture loss while producing antibacterial compounds. The result was meat that dried slowly without rotting. The process began with light salting, followed by controlled exposure to air. Once the protective mold established itself, the meat could hang safely for months. This method required careful observation, not machinery. Today, similar techniques are used in traditional charcuterie, and with proper hygiene and temperature awareness, they remain viable for off-grid living. In Southeast Asia, rhizopus mold transformed cooked soybeans into tempeh, a food that resists spoilage far better than plain legumes. The fungus binds beans together, neutralizes compounds that block mineral absorption, and creates a solid cake that can be dried or lightly fermented further. The steps were straightforward. Beans were soaked, cooked, cooled, inoculated, and kept warm until the fungal network formed. Once established, the food entered a stable state. This method remains one of the most accessible fungal preservation techniques for modern practitioners, requiring minimal tools and no refrigeration. The power of this method lies in ecology rather than chemistry. Protective fungi dominate their environment quickly. They alter pH, consume oxygen, and produce metabolites that suppress competitors. This creates a self-maintaining system. Once established, it resists contamination. Ancient people did not need microscopes to understand this. They just trusted results. Food preserved this way tasted better, lasted longer, and, caused fewer illnesses. For anyone interested in food security, fungal preservation actually offers some pretty practical advantages. It reduces dependence on energy, improves nutritional availability, and, provides redundancy when refrigeration fails. Fermented grain pastes, mold-protected cheeses, and fungal-bound proteins can all be stored in cool spaces without constant oversight. These are not experimental techniques. They are proven systems that, honestly, sustained civilizations. Refrigeration centralized food preservation into a single system. When that system fails, alternatives are rare. Ancient cultures never relied on one method alone. Fungal preservation was one pillar among many. Recovering it does not mean abandoning modern tools. It means restoring balance. If this deep dive added something real to your understanding of how the past still feeds the present, subscribe to Past to Lev. Share this with others who value lost knowledge and help keep these time-tested skills alive. The old ways were not primitive. They were precise, resilient, and still waiting to be used. Past to Live.